morning, everyone. So it's my pleasure to try to wake you up today, or see if I'm successful or not. I don't see any tomatoes in the audience, so I should be okay in that respect, too. So, yeah, let me grab this clicker. I'll be talking today a little bit about some updates for solving problems with InfiniteOpt, as well as with ExaModels, which is why I got a bit extended. So we'll go into all that today. With the ExaModels stuff, that is all work done by, led by Sung-Ho Shin and Francois under the supervision of Mihai when they were both postdocs at Argonne National Lab. Both have moved on to become professors, but so a lot of this work comes from them with regards to ExaModels. Okay, so I'm going to talk about InfiniteOpt a little bit for those that aren't familiar, just to get a little bit of introduction. Then we'll talk about ExaModels, and we'll talk about how the two have been married together in InfiniteExa Models. Okay. So, infinite dimensional optimization. For the abstraction behind InfiniteOpt, we kind of have four core elements to it. The first one being what we call infinite parameters. These are just simply the things that index continuous domains of your decision making. So you can think of time, uncertainty, space. So here you could think of, for example, like if we were thinking of a disease control problem, time as that index is dynamics, and maybe uncertainty having to do with infection rates of some new disease. We don't quite know what the infection rate is. Maybe it's normally distributed, perhaps. Then we can have infinite variables. These are constantly the decisions we're trying to make, and these are indexed by infinite parameters. So you could think of, for example, like the population of infected individuals at a certain time t with a realization of an infection rate xc. In other words, we're optimizing functions, shaping functions. I could have called this functional opt, but InfiniteOpt sounds cooler, and that is important. Okay. Next, we have differential operators. These just help capture the rate of change of a variable. So you can think of things like partial derivatives with respect to time, as this comes up for like ODEs or PDEs. We could also have like Laplace operators or stuff like that. We also have measure operators. These kind of help summarize variables over a particular infinite parameter or continuous domain. So think of how if you have like an integral over time, it'll kind of summarize any dependency a function or variable has over time, kind of collapsing it down to kind of one summarizing value. So this is what integrals do, expectations, risk measures, these types of modeling objects. Okay, so the unifying abstraction for infinite dimensional optimization, that's behind InfiniteOpt, kind of takes infinite parameters, infinite variables, differential operators, and measure operators, gives us a way to model problems in stochastic, dynamic, and PDE constraint optimization, or combinations of those. And all of this is then what enables and is behind InfiniteOpt. Okay. That gives us a way to model these problems, but we still have to solve them. So the way we think about this is through transformations. So a common way to do this is what we call direct transcription. In other words, you have like discretization points for each domain. We call these support points to be more general in InfiniteOpt. And so you can just project your problem onto those points using appropriate numerical approximation schemes along the way. And then you can get a finite dimensional optimization problem that you could then pass on to your favorite solver that MOI supports. And we have over 50 to choose from, which is pretty cool. But you could also think of other ways of solving this. So for example, you might end up using a method like something based on the method of weighted residuals, where instead you project your problem onto a series of basis functions, and then you can represent it in terms of the coefficient variables that accompany each of those basis functions. And that's another way to get a finite dimensional approximation of your original infinite dimensional problem. Okay? So transformations is the way we think about solving these. So InfiniteOpt, then, I presented this a number of times now at JumpDev, but basically it implements that abstraction, gives us a wide way, it helps us model a wide range of problems, and gives us a way to, as I'm going to talk about today, accelerate the solution of those problems. I would argue it has a very intuitive interface. It's also highly performant relative to other similar packages out there. Also, unlike many open source projects, it has very good documentation. Not quite to the level of Oscar's work with JUMP, but it's, it's getting there. This just gives you a little kind of flavor of the API. So you can see there we're defining a stochastic ODE with a chance constraint and just a little toy constraint on the side there too. It has quite a few downloads. This is like per month, and it's used by quite a few different entities and people I didn't quite expect it to be used by. So if you haven't tried it, QR code's there. You can give it a look. To actually solve these problems, what we do is we have this transformation paradigm. So we have this infinite model, which is the core object. We apply a transformation to it to transform it into some sort of what we call a transformation backend, that then we have an API for those two to kind of seamlessly integrate into each other, such that the user doesn't really even need to know that that backend exists. So this is an extensible API, so you can go in there and if you wanted to, add a new way of solving these problems. By default, we do automated transcription. So we have a backend called transcription-opt, which has a bunch of different approximation schemes like orthogonal collocation, finite difference, Gauss quadrature, etc., that will discretize these models and then solve them as jump models. It's not really a fair comparison, but if we compare just manually hard coding those formulations against having InfiniteOpt automatically make them for you, against jump, we scale relatively favorably. Not really a fair comparison to do, but it's kind of cool to see that we can even make that comparison. We were proud of the order n scalability because similar tools would tend to order like order n squared, so getting linear scaling was pretty cool. So actually solving these with transcription opt then, what we do is we apply that transformation to get a finite jump model. We're applying these discretization schemes. We have a whole bunch you can pick from. But a key thing I want to point out, and this will kind of motivate today's talk, is the repeated structure that's inherently there. So if here we have this little toy constraint, sine squared of y of t is less than or equal to 42, the answer, life, the universe, and everything, repeated over the time horizon. When we discretize this, though, we basically get the same algebraic form repeated for as many time points as we choose. So if we have 1,000 time points, we get 1,000 of these constraints that all basically look the same, just indexed at different time points, right? The thing is, traditional modeling languages like JUMP, PyOmo, and others don't directly capture this, right? They'll just actually enumerate all the different constraints you're going to have, and then do the sparse automatic differentiation and build up your AD routines to call into the solver, and we don't necessarily exploit that repeated structure. So the question we had is, given that InfiniteOpt has this structure, can we leverage that structure to accelerate the way we're solving these problems? Okay, so transitioning, we're going to talk about a framework that will ultimately make the answer to that question yes. So this is ExaModels, the work of Sung Ho and Francois. So traditional nonlinear optimization software like IPOpt relies on basically you have your model formulation. You might model in like AMP, Jumple, Casati, PyOmo, right? That models the problem, also comes up with automatic differentiation to get you the derivatives you need, typically sparse. Then you pass it on to a nonlinear solver like IPOpt. And that also might do some line search stuff. And yeah, I won't go into the details of interior point solvers, but it's up there. And then those, as we're going through their algorithms, are going to rely on a sparse linear solver, maybe like MA27 or whatever you like to use, along the way to make that all possible, primarily in dealing with that Newton step. So this is kind of how the whole pipeline goes together when you want to solve nonlinear optimization problems of IPOpt or similar. Okay, these were developed a little while ago, and these haven't really utilized GPUs at all. But that wasn't really an option back then. So the question that they had is, can they take something like this, but somehow make it work entirely on GPUs, the entire pipeline? Okay, which is, there you go, the statement right there. So how does the GPU work? So it works on this paradigm called SIMD, which is single instruction, multiple data, where you have kind of this dedicated device memory, but it's kind of a slow interface. So basically, if you can get it into this abstraction, you can run simple commands on a lot of data very quickly, but if you need to do more complex things, it might not be the best fit. So this is kind of showing how you can have a bunch of GPUs on unified memory with things like NVIDIA Grace Hopper. The thing is, trying then to adapt algorithms that have been run on CPU to run effectively in GPU is non-trivial because the architecture is fundamentally different, and what was good on CPU, which is more flexible, isn't necessarily going to work on GPU. So a lot of software engineering and algorithm redesign needs to happen. So what they came up with was the SIMD abstraction for NLPs. The observation here is, again, many large nonlinear optimization problems often have these repeated algebraic patterns. So for instance, they work a lot with the ACOPF problem. Here, this formulation is basically the same if you have like a power network of like a city or a state or a country. Just it ends up getting repeated that many times, right? But the algebraic structure itself doesn't actually really change, and there's not that many. I can fit it on one slide. It's not that many equations. So they came up with this SIMD abstraction, which basically captures this single instruction, that structure, F, over multiple data, so the data that repeats this. And hopefully you have a small number of patterns. That's the key assumption they have. This might be like, I don't know, 20, 30, maybe up to 50 constraints that have these unique patterns. And so their native syntax is you can have like a constrained object, right, with the instruction, the basic algebraic form, over some iteration data. This didn't translate well. Oh well. Format-wise, that repeats that structure, so some sort of iterator. And so for each pattern, they compile an AD kernel that can then be executed over the data, so they can have parallelized AD routines, and they only have to compute a few of those for the different patterns that they find. Okay, so this is a benchmark they did over across the different architectures, and like Jump and Ample, versus using ExaModels, which implements this, to see how they did. Come on. So there with the arrows, you can kind of see the stuff that is ExaModels. Here, to be higher on the graph is better. And as you get further to the right, you have more and more variables. So as you get more and more variables, the relative benefits get better as well. And what was also cool is this was compatible with all major GPU architectures. You can list on AMD, Intel, NVIDIA, and it worked on all of them. So they can do... I'm sorry? I think so. Yeah. Yeah, it's built on like the Julia GPU kind of framework, right? Which has some nice packages to make it GPU independent. So yeah, this gives us a way to do sparse automatic differentiation that's efficient across both CPUs and GPUs. You also get speed up on CPU because again, we're having this repeated structure and I have to keep computing it over and over again. So even on CPU, you see benefit. Okay, so then to actually go about trying to solve this in GPUs, this could be quite a few slides. I'm not going to go into deep detail on this today. If you want to know more about this, he gave a presentation on this. Is on YouTube a few months ago for the same slides. But basically here, we need algebraic modeling systems, the solvers, and the sparse linear solver. So ExaModels provides the way to model it and get the sparse automatic differentiation that you need that can run in different GPU architectures. MadNLP, they've done that up so it can do these lifted and hybrid KKT systems entirely in GPU. They had to do some lifted systems basically to make sure the matrix is positive semi-definite so it's compatible with GPUs. Not typically a problem on CPU. And recently, NVIDIA put out this CUDA, or it's a CUD SS, a kind of experimental package that allows you to do some linear algebra solvers entirely on their NVIDIA GPUs. So while ExaModels can do any GPU, in order to this whole pipeline entirely on GPU, we're currently limited to NVIDIA only. The hope is there'll be a more generic routine that comes out in the future that might support other architectures. But at least NVIDIA is fairly popular, as their stock seems to show. So, okay. So this is a benchmark they ran with some of their ACOPF problems. Whole big table here. The cool thing, though, is the bottom there. They have this 80,000 bus example, the entire Eastern interconnection, and that ran on GPU in under 20 seconds, which was significantly faster than the CPU implementation over here, which was 207 seconds, so an order of magnitude faster. Okay. Now, one thing to note is there are some stability issues with the GPU solvers, so they only solve this to a 10 to negative 6 tolerance, not like 10 to negative 8 or so, as is more standard of IPOpt. And a lot of problems we have found you can solve to a better tolerance, but to be more conservative, they just did 10 to the negative 6. Okay, we also have this distillation column problem. I'm a chemical engineer. This is for basically model predictive control. So here, a thing to note is when we're running this on GPU, is a significant amount of our time relative to solve time is just in initializing the problem on GPU, so kind of getting everything set up and ready to go. So the good thing is that's just a one-time thing. So if this is like an online control context, this can just be kind of an offline upfront cost. And then we can just reap the benefits of the fast GPU solves on any repeated solves. So this type of framework is quite nice for doing optimal control type work where we just want to solve similar problems again and again. And there you get quite a bit of benefit relative to traditional CPU routines. And this has nothing to do with warm starting. This is just the fact that we don't have to initialize the GPUs every single time. If you warm started, you'd even get more benefit, right, because you give it a better initial guess. So we have found in this context that we can get pretty efficient and reliable results using this entirely GPU pipeline for solving NLP problems. Okay, some remaining challenges they have, mainly they rely on this sparse Cholesky factorization. Currently, that's only possible to do with that NVIDIA-specific solver, so hopefully some more generic solvers that can kind of bridge the gap between the other GPU architectures might get developed. There's some works in progress, and if and when that exists, this framework will then work on basically any type of GPU supported by that, so hopefully NVIDIA, AMD, and Intel as well. They've also done a lot of recent work looking into multi-GPU workflows, so if you have like that NVIDIA Link stuff, they have like at Argonne like a system of, I don't know how, like 100 GPUs, I don't know exactly, but a whole bunch. And so they're trying this as you parallelize this on a whole bunch of GPUs, how much kind of speed up do you get? And they've found that it works quite well. I don't have those results with me though. Okay, to connect this back to MOI, so that whole framework is built on the NLP Models framework. Okay, so it's compatible with kind of the Julia Smooth optimization environment. So to make this compatible with JUMP, they have this extension called ExaModels MOI that behind the scenes, basically to end up using it, all you have to do is you get this sort of ExaModels optimizer object that you can just put in a JUMP model. And then what it does behind the scenes is it will iterate through that JUMP model once it's made, look for any common algebraic structure by binning, and then it'll construct an Exa model and then proceed forward as normal. As a result, it doesn't really have that global structure to begin with, and because it's kind of doing this generic search, it doesn't necessarily make the most efficient version of an Exa model, but it works. It's still experimental, so it has a few quirks, but you're welcome to try it out. So in the end, ExaModels and MadNLP gives us a way to accelerate solutions with problems with repeated patterns. So here on the left, we've got IPOpt, we give it a head start. On the right, we've got the GPU framework. That's done. And we're going to wait for IPOpt to catch up. Still going. It's okay. The important thing is to finish the race. It's going to get there. It got there. Congrats. So you can see it makes a pretty big difference for these types of problems. The only problem we run into is translating now infinite opt problems that we've discretized to this SIMD abstraction. It is possible to do it by hand, but it's fairly non-trivial, especially if you want to do things like orthogonal collocation over finite elements. Trying to make that work with their abstraction, because it doesn't really work with sums that well, becomes fairly non-trivial to do. Also, again, with that MOI backend that they have, it kind of ignores the repeated structure. You have to do a lot of extra work to get these suboptimal EXA models. So what we've done then is we've made this backend to InfiniteOpt called InfiniteExa Models that will solve those problems. Okay, so InfiniteExa Models bridges the gap between InfiniteOpt and EXA Models. So this gives us a very nice intuitive interface that is InfiniteOpt and automates transcription. So all the library of transcription methods that come with InfiniteOpt will now work with EXA Models. Okay. And because we have this inherent repeated structure stored in InfiniteOpt, we can leverage that to drastically reduce model creation time. We actually found we can make it basically independent of the discretization size. And this gives us a way to do it actually even more efficiently than you could by manually making the EXA model object in most cases. So how does this work? So this directly supports any JSO NLP solver. Again, EXA Models is based in NLP Models, so you can use their flavors of NLP, IPOpt, or KNitro. We have this object in InfiniteOpt, so called EXA transcription backend. So what you do is you have your infinite model. You just give it this EXA transcription backend and whatever solver you want to use. That's it. After that, you just define your infinite model as normal. Nothing else changes. Behind the scenes, it'll rapidly translate this into a very efficient EXA model. And we have found that the model build time becomes essentially independent of the discretization size because we're just making this kind of generic pattern. So if I have 1,000 samples or 1,000,000 samples, it doesn't care. Obviously, the solve time is going to change, but the model build time does not. It changes minorly because the data dictionary gets a little bit bigger, but it's negligible. So to try this out, we tried this using solving with jump, ample, EXA models with their MOI backend, and InfiniteExa models on CPU and GPU. We also did the CPU on like the best AMD EPYC processor we could find, and we did the GPU on just kind of an old A6000 NVIDIA GPU we had laying around, so trying to weight the odds in favor of IPOpt. We have a two-stage stochastic program. It was just an stochastic ACOPF, optimal control problem to control a quadcopter, and the stochastic optimal control problem, which is managing disease control with some uncertainty in it. So these are the numerical results with CPU. So even on CPU, we've noted with this repeated structure, we get significant speed up on the automatic differentiation. Quite a bit faster in both EXA models and InfiniteExa models. Again, we do a little bit better on InfiniteExa models because we have a better EXA model structure. That's more efficient than you get with kind of the pessimistic ones you come up with the other interface. Our build time, though, goes drastically down because we're leveraging these repeated patterns. We're significantly faster to build the model. And again, if we increase the sample size, that time doesn't really change. The other times will change. And again, this is all implemented by just having that transcription backend, and that's all you have to do. Okay? On GPU, relative to EXA models, our total time goes way down. Again, these times are significantly faster relative to the CPU times. And we are even faster, again, because our build time is significantly less. That's our main benefit of using InfiniteExa models, and our AD is also is also pretty good. So overall, we're getting orders of magnitude speed up relative to CPU. And again, this is not accounting for this includes the initialized time. So if you do any repeated solves, like an optimal control setting, this goes up by like another order of magnitude faster relative to CPU. So we get some pretty significant speed ups. And again, this is implemented. All you have to do is import these packages. They have that back end with your CUDA back end, and it just works. One cool thing is I ran this on my laptop. I just installed these packages. I didn't have any NVIDIA stuff set up at all, no CUDA. These packages automated the install of all the CUDA stuff, and it just worked. So within about 4 minutes, I was able to solve this on GPU without having to really do anything special myself. So that was pretty cool. So if you want to try it out, here's QR codes to all the different things from today. And I haven't quite released InfiniteExa Models yet, but you can download the master branch. It works. I want to add some more tests before making an official release. But that's what I got. QR codes on this next slide. So with that, happy to take any questions. Thank you for staying awake.